Hola, me llamo David Liu, and we don't have to go through the core basics of navigation because that's already been done for me, but I've spent a lot of time working on navigation over the last couple of years, maintaining the ROS navigation stack, but that's not really what I wanted to do when I started off. I actually started off in HRI. Ooh. Doesn't want to mirror displays at the moment. So I actually started off in HRI, and I was very much inspired by this paper that came out of Willow Garage towards the very beginning, talking about using animation principles to get to increase people's perception of the robots. And so what they would do is they animated it to make it do a number of different things. And I wanted to take what they had done and implement that using the nav stack. So one of the things they did was have it look in the direction it was about to go. But that required getting the global plan, looking in that direction, and then start driving. But the way move base works is it would automatically get the global plan and pass it directly to the local planner. And so there was no way to get it to look that way before moving. And secondly, they had it react to whether or not the robot succeeded in its navigation. And that was tricky because if you would need to know if the robot failed, how it failed, and when it failed. And with the current navigation stack, you can only get if it failed and not how it failed or when it failed in the context of the larger navigation action. And finally, for all of this, it wasn't as much a part of that paper, but you also need to plan around people using different type of cost map, or plan in a way that people were able to understand what it is the robot was doing. And all these operations tend to be very difficult just because customizing the planners that are a part of the navigation stack is tricky. So my point with all of this is that the current navigation stack does really well getting you from point A to point B. But there's a lot more to operating robots in this way, and context is key. You have to be able to customize your robot's navigation behavior for the particular context that you're going to be operating in. And that requires a lot of customization that the navigation stack is not ready to allow at this point. And so what I'm going to be talking about today, start off with just sort of the state of the navigation stack as it is, talk about the new interfaces that I've designed for writing planners, talk about a new global planner that I've written, and Locomotor, which is our move-based replacement that ties all the pieces together, and then at the end I'm going to touch on ROS2 briefly. So I maintain the current navigation stack, and so you might be asking, why the fork would you want to make a new version of this code? Well, in this slide you can see that the current number of navigation stack forks is 734. This is up a couple hundred from when I presented a version of this slide last year. It's actually up 3 since I made the screenshot. And what this says to me is that there's a lot of good stuff in the navigation stack. And there's a lot of stuff that people almost find working about it, so that they'll, instead of actually using it as is, they'll take the code, make their one small tweak, and then use that, and then their navigation works. It's hard to swap out those single little components, so it's much easier to just make a wholesale fork. And then sometimes people will push those changes back upstream. And that's great. I've done that a number of times. But the problem with that is that we end up with the 30 trillion parameters that are currently in the navigation stack. And we're trying, part of the problem is that you end up with a system that can be configured for anybody's purposes. And that includes a lot of corner cases. And it's difficult to replace small parts, so you get a lot of corner cases, makes it very hard to test. And the other reason why I want to make something new is because I know that a lot of people rely on this navigation code. Not only the 734 people who have forked it here, but a lot of organizations have forked it privately. And breaking things here would cause trouble for them elsewhere. So I don't want to break what's already there. But I do have a number of problems with the navigation stack as it is. So unlike the last talk, the navigation stack really only affords for planar navigation. That is an X, a Y, and a theta. It doesn't really care if it's off the ground or lying on its back. that extra pose information is redundant and makes operating within the navigation stack more difficult. The nav core interfaces have generally not been updated in almost a decade now, and there are some serious limitations that I'll talk about later. COSMAP 2D is great. There was some great work done at Willow Garage a number of years ago by a guy named David Liu, who put COSMAP layers into the COSMAP. But that does force you to use COSMAP layers, and sometimes you really just want to throw some values into a grid, and so it adds a lot of overhead. Also, COSMAP 2D and a lot of the related packages use occupancy grids, which means that you end up, which is fine, except for most COSMAPs have 256 unique values, whereas occupancy grids really only allow you to transmit 0 to 100. And that's problematic in a number of different places, widely regarded as a bad idea. As far as global planners go, the standard that people use is navfn, which is great, except for it's prematurely optimized in a couple of different ways. There's a couple of magic numbers in there that took me forever to understand, and it's hard to edit. I tried to edit it once, and I made a package called Global Planner, which is a lot more modular, but it has bugs, and there's actually some simple navigation, simple path planning examples that don't work in that planner, so it's not great. As far as local planners go, I talked mostly about this last year, but they're difficult to debug and customize. And MoveBase. MoveBase is central to all of the operation of the ROS navigation stack. But for most purposes, it is a black box where you put your goals in and hope for the best. And the best that you can hope for is changing the list of static recovery behaviors. But those same recovery behaviors will be run every time, regardless of the method in which your robot fails planning. And that results in not very intelligent contextualized behavior. So in the work that I'm presenting today, I had a couple of design methodology where I really want to build reusable pieces. It's all meant to be extensible. I want people to be able to take pieces of what I've done and hack it apart just as I would, and hopefully understand how each of the pieces operates, meaning no black boxes. Chief among those reusable pieces is a data structure that occurs multiple times in the navigation stack, which I'm calling navgrid. A COSMAP is really this grid-based representation where we assign a value to each cell in a grid. This is used in COSMAPs, but it's also used in the global planner in a couple of different places, as well as the local planner for storing different types of information. And so I've created a data structure here meant to be reused, where you declare where the grid is based on one of these navgrid infos, and then you can use it in a number of different contexts. And so the data storage here is all abstracted so that you can have it be backed by a standard vector or any other type of data storage. The typing is template-based, so you can stick in floats, unsigned chars, classes, whatever you'd like. There's a whole library for coordinate translation, from translating from world coordinates to grid coordinates and back. There are new message types that don't suffer the setbacks of occupancy grid, called navgrid of chars and the related updates. And finally, this is inspired by the work of the grid map people. There are also iterators that work on these that are easily reused for a number of different operations. And so this actually forms the basis of one of the new new plugins I made. And so with these new interfaces, it's plugins all the way down. When all you have is a hammer, everything looks like a nail. I love just adding plugins to wherever I can in the nav stack. So not only were the planners already plugins, I made the COSMAP layers also be plugins. Last year I talked about DWB Local Planner, which was based on plugins, and now we have some more. So now I've made the COSMAP itself a plugin. And so as long as it adheres to this interface, you could use any type of COSMAP in these new interfaces. So just a couple of quick points. This is based on navgrid, but it uses unsigned char, much like the old COSMAPs did. And that's for a number of reasons, data storage concerns being one, but also just having a limited number of unique values is also important. There are no required TFs. The old COSMAPs required that certain transforms be present before you could actually get them to initialize. Here that's not true, and it makes testing much easier. There is no built-in update thread, so you can control how often the cost map updates. And you can use any update algorithm underneath, therefore not forced to use the layered cost map. And then I also added this option to track changes within the cost map so you can know how much has been updated. Furthermore, all of this is compatible with the previous version of CostMap 2D ROS so that you can still use new plugins, the voxel layer, and things like that within this interface. So last year I talked about DWB Local Planner and all the different components which were plugins so that you could customize it to your own needs. Now with the new Global Planner interface, it's very similar in that it also uses these nav2D messages which eliminate all of the 3D information that's provided, but also instead of just returning a Boolean for whether it succeeds or fails, it throws exceptions so that you can get more contextual information about why it failed. And so we have a new global planner, which is called Deluxe Global Planner. That name was suggested by one of my colleagues at Locus Robotics. And the two major plugins we have are the potential calculator, which is where you put in your graph theory algorithm of choice. So the ones we have right now are Dijkstra and A-star. And then you have the traceback that generates the actual path from the grid, and there's a number of different ones that either adhere to the grid or have a nice gradient. And so here's just some examples of what those paths could look like. Here are the 4 neighbor-based ones, the 8 neighbor-based grid ones, and then the gradient ones. But the real ones there's a lot of different instantiations of this that you can make depending on which plugins you use, which A-star heuristics you get, but you can get something fairly close to the optimal here. And so you might be asking why I feel confident releasing a new global planner when the one that I previously made has some bugs in it. I also made a class called Global Planner Tests, which is based on the NavCore 2 Global Planner interface, and will run unit tests to make global plans from every free cell to every other free cell in a number of given maps, and run those as unit tests so that you can actually make sure that your global planner conforms. All right, but the key component here is that manages all of this is MoveBase. And so, as we talked about before, there are 4 components, the 2 planners and the 2 cost maps. And really, all MoveBase does is it takes the global planner from the global plan from the global planner and delivers it to the local planner. At least that's what's supposed to happen when everything's going right. And the complexity comes from trying to recover when the planning fails. And that's when you get into the number of recovery behaviors. One of the key limitations here is the fact that there's so many different threads in MoveBase. There's one for each of the cost maps to update, and then each of the planners is also run in a separate thread. And that creates a lot of different problems, as talked about in Ingo's talk last year, where you can have robots not reacting to sensor data because of all the different threads and end up crashing into things. So our replacement for this is called Locomotor, which is an extensible path planning coordination engine, which allows you to define what exactly happens when your path planning succeeds or fails. And it's built on the same NavCore 2 interfaces that I talked about before, and it leverages ROS callback queues in order to be able to handle the different threading of the events. So just as an example, you start off with a request global plan that will put a new event onto the callback queue, which runs make global plan, and that event will trigger one of 2 other events, either on new global plan or on global planning exception. And you can extend these to define exactly what happens in each of those cases. And there's similar events for the local planner as well as updating the cost maps. And so an example of how this would work, you can make a single-threaded version of Locomotor, where you start off when you get a goal, you say, do a global cost map update, and from there, that will trigger a callback to the make global plan. When that succeeds, that will start a timer, and the timer will trigger and cause a local cost map update, followed by a local plan update. And then that will loop around, and the timer will trigger again, and you'll get your robot to drive along the path. Now this is something, the single thread version, something that you can't do in MoveBase. But this is what happens when everything is working well. And what you want to be able to do is control when things don't go well. So how do you deal with failure? So let's say your global planning fails. It might cause different types of exceptions. So it might cause an invalid start pose exception, or an invalid goal pose, or a number of other different exceptions. And now you can catch that exception and cause different behaviors to happen depending on the type. So if the start pose is invalid, maybe you want to clear the cost map and try again. If the goal pose causes a problem, then maybe you want to choose a new goal and react in that way. And so this is just an example. You are allowed to extend this class and change these mappings to fit your particular context. You can also get something with 2 threads. So the previous example, you could only get one global plan. Now we start a timer to make the global plans. And when we get a global plan, we not only trigger the local planner timer, but we will also loop back and start planning again. And that's all done on one callback queue. And then on the other callback queue, the timer starts and does the local cost map update and local planning. And this way you get both the global plan and local plan updating continuously. And you can take it further. You can make 4 different timers for each of the different components. This is much like what MoveBase does, where each of them runs on a different update cycle. And in fact, we made a replacement specifically for MoveBase where you can drop it in, called LocoMoveBase, that allows you to use your previous cost maps, so the same cost map 2D ROS, but then also load NavCore recovery behaviors, so that when, for example, your global plan fails, on any exception, it will go through the static list of recovery behaviors, just like MoveBase would. One of the other features is there is a plugin mux. This bit isn't specific to NavCore 2, but it allows you to load multiple different plugin-lib plugins and switch between them either via C++ method or ROS service. And one thing that enables is that when you get an exception, you can choose to switch your planner. So if your local plan fails, maybe switch to a different local planner that you think could handle that. And just to go back to the first example that I showed, we also, here I've extended this so that when the global plan is made, then we stop, look in the direction of the global plan, and then we start the timer. So just as a way to customize what's going on. So MoveBase is also centered around this MoveBase action, which I find wholly useless for pretty much anything other than the core idea of starting the action and ending the action. You provide it with a target pose, and it occasionally will give you a base position update. I have this new locomotor action, which you give it a goal, and you get much more robust information back. You're not forced to use this. You can create your own actions as well. And so while we're talking about the next generation of things, we are currently working on a full reimplementation of the nav stack with the planners that I talked about, as well as locomotor, but also a new implementation of the layered cost map and cost map layers that conforms to that cost map interface that I talked about before, as well as NavGrid server and saver and things like that. And our goal is to have a ROS 2 version of this out by the year's end. This is work done in conjunction with Matt Hansen and his group at Intel, who are currently spearheading the ROS 2 navigation efforts. And with that, thank you very much.
Do we have any questions for David? All right, there's one coming down.
Thank you for the nice talk. Since you adapted many ideas from MoveBase Lex, where would you say is the main difference? And okay, you only support 2D, right? Is this right? You only support 2D map representations?
Yeah. So one of the ideas of some of other navigation implementations right now is to support full 3D, being quadcopters, what have you. My approach is to do the one thing very well, hopefully, and run in just the 2.5D XY theta space. In its far as move-based flex goes, there's a lot of, I think it's been a shame that everybody has been forced to use move-based in the past, and I think that the fact that there are multiple implementations of how to run navigation out there is key. But it's, this is something that I've had percolating in different forms for a number of different years, and I think having different ways to adapt running the global and local planner is going to be very useful going forward.
And are there any plans to have a standard navigation stack for robots in 3D navigating or navigating in 3D?
Personally, no. That is not something that I'm working on. It's not something that my company has robots capable of doing at this time. I always take gifts of quadcopters, but no. But no, it is not something that I'm looking at right now.
Okay, thanks.
I'm bad enough at the existing dimensions.
All right, thank you very much.
Thank you.